Floor here today. All right, I'd like to introduce Shane Foubister for our next talk. Go ahead, Shane, and you could just use the arrows.
Perfect, just next like that.
Yeah, and there's the laser.
Ready. Hello, everyone. My name is Shane Foubister, and I am with the Geoscience and Source Water Protection Unit at the City of Ottawa. And today I'm going to be presenting some of my master's research, which, thanks for the intro, Laura and Kayla, covering some of the background stuff for me. And I'm going to be going through a little bit more detail as to our high sampling density areas in Eastern Ontario. Specifically looking at the relationships between bedrock topography, drift thickness, kind of the regional groundwater flow system, and how that impacts our groundwater geochemistry across the area. So without further ado, we'll get this going. Before I start, just a couple acknowledgements. Special thanks to Dr. Ian Clark at the University of Ottawa, Stu Hamilton and the folks at the OGS, and Tessa Diorio at the City of Ottawa for really getting this program going. And of course, my fellow MSc students who really did a great job of laying the groundwork for me before this. And all of our volunteers that let us strangers into their homes to check out their pressure tanks and collect their water samples and look at their treatment systems. Special thanks to them as well. So I won't spend too much time on the background, as I feel like most of you probably have a pretty good gist of that by now, thanks to the previous presentations. But this program was implemented to help develop the Aquifer Capability Screening Tool. We have a pretty significant portion of residents in Eastern Ontario and the City of Ottawa that rely on groundwater. We have a couple of municipal wells and a lot of folks in rural areas that rely on it. And there's a lot of really weird stuff in Eastern Ontario when it comes to our groundwater geochemistry, attributed to a very complex geology in the area. And special shout out as well to Alex Lemieux for doing some fantastic work looking at the interrelationships between methane, the halogens, and some of those glacial-marine deposits that Laura had talked about. So why is Eastern Ontario so weird? Well, we've got a lot of carbonate and shale units. However, there's a lot of complex issues with faulting and things that have taken place during the breakup of North America and the opening of the Atlantic Ocean. So there's a lot of faulting within the Ottawa Valley, and a lot of the bedrock in the area is primarily Paleozoic sedimentary units, as well as some shale units as well. Our surficial geology is quite complex in the area as well. You can see effects of the Wisconsin glaciation, the incursion of the Champlain Sea, and then a lot of reworking of those sediments from the massive Proto-Ottawa River between about 10,000 and 4.7 thousand years ago. The hydrogeology for Eastern Ontario, most residents in the area rely on the contact interface aquifer across the area. This is because of its high yield. It's also very similar to the Basset-Laurentide aquifer system in Western Quebec, who Clouthier and others have done a lot of great work characterizing. And you can see the conceptual model up here in the top right-hand corner. Essentially, as Laura had mentioned, we have recharge occurring in our topographic highs that are unconfined with limited drift cover. And as we move deeper into those bedrock depressions, we get more highly evolved groundwaters, as well as more impacts from some of the processes that Laura had discussed. I won't spend too much time on the sampling methods, as again, this was already covered, but effectively it's following the same methods for the ambient groundwater geochemistry project, but at a higher sampling density. We also ran a call center and did a bunch of news blasts to get volunteers. So that was a fun week or so with the phone ringing constantly, but it was a great program, and to date there's been about 3 studies done in the City of Ottawa, and I think we have 1,800 or 1,900 folks on the wait list. So there's a huge interest from our residents around Eastern Ontario in their groundwater, which is great. So a little bit of background, I'm sure a lot of you guys know about the MRD 207. You know, there already is an existing bedrock topographic model. However, in the early stage of my work, I was able to identify quite a few issues in certain areas, especially in Alfred and Plantagenet, where certain well records didn't quite match up with the existing bedrock topographic model. This is because of the fact that there's a lot of issues with well records in Eastern Ontario. I think when they first implemented them, not too many drillers cared too much about filling out their well records. And as you can see here, this is kind of my general workflow for developing my own bedrock topographic and drift thickness model, using a lot of the steps that George Gow had identified in MRD 207, and doing a lot of manual investigation and adjustment of those well records in those low density areas where the wells had the highest weight on the output model. As you can see here, here's our distribution of well records across Eastern Ontario within my study area. There's about 20,000 of them or so at the time when I was doing this. And we've got about 230 known bedrock outcrops that were used as well to help better constrain those areas of thin drift. Some of the general improvements that were done was first a lot of filtering and cleaning up of those well records to remove well records that effectively had null information, inconsistent data fields, and then manually investigating those records in those low density area. And another step of QA/QC was done through this where I essentially standardized and consolidated and classified all of the overburden materials within these well records, and then compared that with the depth to bedrock to make sure that the well records that I was using in this model had a complete picture from top to bottom. And some of the limitations, again, as I already alluded to, there's some issues with reporting and lack of information in some of those well records, and there's loads of location issues as well with that. We can see here some of the results. So this modeling was done in ArcGIS Pro using the 3D capabilities of that program. And this is the output. We're looking at here the bedrock elevation with a 50 times vertical exaggeration. We have the Ottawa River running kind of along the top of that model there. The city of Ottawa is just to the top center or so, just above the northwestern uplands, the NWUL. And if you'd like to know more about what these actually stand for, feel free to check out my thesis as I go into a bit more detail on these. A couple of high-level highlights though. The deepest or maximum drift thickness that was identified from some of these well records that were cleaned up was 152 meters, and that was within the Northwestern Depression, just a little bit west of Hawkesbury, for those of you who know your geography in Eastern Ontario. And the deepest bedrock surface that was identified within these cleaned up well records were about 102 meters below sea level. And so that's quite deep. And I also did a quick QA/QC to see, effectively, once I had spent, I don't know, 100 or so hours cleaning up those well records, looking back and saying, okay, was this worth it? Was it worth going and spending all this time? And there's about a 32% improvement in that data consistency. So the raw input data, that depth to bedrock field, matched the interpolated surface about 32% better from that cleaned up well record data set. So now that we've established that, it was time to then look at some of those bedrock topographic and drift thickness maps and compare them with our, effectively our bedrock geology in the area. And some of those gray colors you can see in the center image there, those are some of our shale formations, the Carlsbad, the Billings, and those in blue are kind of more the carbonate-based ones. Something that's interesting as well that came out of this, that pink, that little bit of pink there that you see in the center image, that's actually the Queenston Formation. It's the only area that it's known to outcrop in Eastern Ontario. And you can also see that that coincides quite nicely with the bedrock ridge, which you can see in the leftmost, which is drift thickness, that green area that's thin drift. And it coincides quite nicely with that bedrock ridge. Running a quick query as well to look at all of those well records that were retained for red shale. You can also see, which is a very characteristic feature of the Queenston Formation. You can see that those plot very nicely in that area with the Queenston Formation as well. And it also suggests that that Queenston subcropping formation also may extend a little bit more than previously mapped, which is quite interesting. So now that we've established the bedrock topographic and overburden thickness models for Eastern Ontario, the next step was then to look at our groundwater geochemistry, look at our higher sampling density to kind of build on a lot of that work that Laura had done. And the data speaks for itself with respect to some of the spatial trends. I will point out that the ones that you see here, all of these points, these are bedrock interface wells. So you may recall on Laura's slide, there's a lot more of them in this area. I pretty much exclusively was looking at our wells that were drawing from either the interface or bedrock aquifers. That was what I was interested in. And we can see some really clear spatial patterns, as Laura had already kind of mentioned, with lower pH ranges in some of those bedrock uplands with thin drift, elevated calcium in those areas, as mentioned by Laura and Kayla, with the dissolution of calcium carbonate because of those lower pH, more acidic waters from meteoric infiltration. And elevated calcium from that as well. And yeah, and as we move forward now, looking at some of our tritium as well as dissolved oxygen, we can also start to see where we are in that early phase of groundwater flow versus the later phase of groundwater flow. We can see that in our bedrock uplands with thin drift cover, we have detectable tritium, elevated content of tritium. And as we move further down into that regional flow system, especially into that bedrock depression in the center there in the green, we start to lose that. And we can also see some interesting trends when we look at dissolved oxygen in those areas as well, with basically there being an absence of detectable dissolved oxygen, which is what we'd expect in those highly reducing settings in the bedrock depressions. And we start to see some of that detectable dissolved oxygen in those bedrock uplands as well. Moving on now to the more highly evolved reducing groundwaters, which were sampled from those bedrock depressions with very thick drift cover, with glacier marine deposits as well. We can start to see some of those trends that Laura had identified with elevated levels of sodium and chloride in those areas, attributed to the impact of saline waters, salinization going on. We can also see some elevated levels of methane and iodide, which complements Alex Lemieux's work, where he was looking at effectively methanogenesis and organic breakdown, releasing that iodide into those groundwaters as well. And as Laura had mentioned, we have some very, very high concentrations of iodide in Eastern Ontario, and that was showcased in Courtney Rogerson's thesis as well. Something else that is always of good value, especially anybody who knows Dr. Ian Clark, is you gotta talk about the isotopes as well, of course, as it helps add an extra layer of information. And as we're looking at our oxygen 18 and our deuterium, we can also see some of these trends as well. Some of the samples that were collected in those upland areas where recharge is occurring, we see stable isotope values that are closely resemble meteoric water. And as we move into those more highly evolved, reducing groundwaters within those bedrock depressions, we start to see more enriched deuterium and oxygen 18 values, up to 4% per mil in some of those samples with high chloride as well, which is very interesting. Something else that was quite interesting from this as well was looking at some of our trends in that transitional area. So we kind of talked about the bedrock depressions, our bedrock topographic lows, and our topographic highs. But there was actually also some interesting trends in that transitional area. And if you think of this from a redox perspective, we're going from more of an oxidizing environment into a reducing environment. And within that transitional area, that was where I really observed quite a lot of the elevated fluoride values. So of the 369 bedrock interface samples that were included in my data set, about 59 of them exceeded the 1.5 milligram warning level for fluoride, and we had about 17 of them that were above the 2.4 MAC for fluoride. Something else that correlates quite well with that as well is phosphate. We have some of the highest phosphate levels in groundwater in the entire province, up to 14.1 milligrams per liter. And any of you who follow the CBC News, a couple months ago, there was an article talking about an exploration company looking at phosphate potential in Gatineau, which is actually just a couple kilometers northwest of my study area. I didn't go into too much detail on this in my work, but it's definitely an interesting trend that I wanted to share with you guys as well. So in conclusion, effectively, the regional groundwater flow pattern across Eastern Ontario is controlled by bedrock topography, overburden thickness, which in turn affects residence times, which then in turn affects the chemistry of the water, again with those elevated calcium chloride or calcium bicarbonate waters in those bedrock topographic highs where recharge is taking place. And then as we move down into those bedrock depressions, we move into more reducing waters, elevated dissolved methane, high levels of iodide, and high levels of chloride as well. And in between, we also see some interesting things with respect to fluoride and phosphate. And conclusions, wild records are great. There's a lot of them. It's probably one of the largest publicly available data sets in the province. They also really suck and require a lot of special time and attention to use them properly. And but I think when you do use them, again, it can provide you insights to where there wouldn't have been otherwise. And just again to reiterate the fact that the groundwater chemistry in Eastern Ontario is very closely linked to that relative position within the regional flow system. And again, I'm reiterating essentially what Laura had identified too, with respect to the main geochemical processes in Eastern Ontario affecting groundwater chemistry being recharge, cation exchange, organic decomposition, and salinization as well. And that will do it for me. But if you guys have any questions, feel free to ask, send me an email, come chat with me afterwards. Always happy to talk about groundwater. So thank you guys very much. All right. If anybody has any questions, feel free to send them out now. Oh, one there.
Thank you. You had tested for tritium, and I'm wondering if you had tested for uranium and if there were any high concentrations of that.
Yep,
that
so
radioactive element.
as part of the ambient groundwater geochemistry project, as Laura had talked about, there's about 99 different parameters. So our data set essentially has pretty much every trace metal, including uranium. However, there wasn't really anything of interesting note. There was a West Ottawa groundwater study done in 2019, and in the west end of Ottawa, there actually is some outcropping Precambrian formations, and there may have been some slightly elevated uranium. I'd have to look, but I do know that that was more of a concern in the west part of Ottawa. Yep. All right. Thank you very much.